So welcome again, everybody. I hope you had a nice coffee break, that you're ready for the next presentation by Fernanda. Fernanda is here, assistant professor at the University of Eindhoven in the group of chemical engineering and chemistry. Nice to know from 1st of October she will also be our TNO colleague in Patton for a few days a week. Also very nice. And Fernanda will take us further into the HIGFLY project. Floor is yours.
Okay, thank you very much, André, for the nice introduction. And I have the difficult task to tell you something about HIGFLY. So HIGFLY, of course, as you already know by now, is a European project that is going to end in a couple of months, where we have been doing some research on development of new advanced biosafs and chemical building blocks. We purposely changed the presentation with, with Daisy, so by now you know what biosaf is, so I don't need to introduce that. But before starting really on HIGFLY, I always think it's nice to start on the why, but I think the introductions before were pretty, let's say, helpful, so I don't really need to explain much. Basically, from this slide, I try to summarize the challenge that we are facing. So we are trying to replace fossil resources, of course, for energy and materials. And on the right side, you see basically a green scenario where we electrify the energy sector mostly as much as possible. But we still see a major role for biofeedstocks, mostly for, let's say, materials, but also, I think from the presentation before we have seen, there is still a place for biomass for fuels. So that's pretty much what I've tried to show here. I don't think, yeah. So here is our, let's say, circular carbon cycle, which of course relies on biomass, CO2, and recycling of plastics. But it's important to realize that this CO2 and recycling of plastics to be recycled, they would also have to be bio-based in order to be this fully circular. So again, very important to rely on biomass. In this picture, we also see, or I also put here, an important role of carriers of energy or carriers of hydrogen, methanol, ammonia. Of course, this is important to accommodate the complex dynamics of the energy sector. But of course, a key ingredient here that I also want to highlight is that we know that to make that cycle possible, there is a lot of energy. So these processes are very energy demanding. So at the end, process efficiency is going to be key. And also, looking at the feedstock picture that we have been discussing in the morning, resource efficiency, so getting more out of what we put in, is going to be important to realize this. Focusing on this, so here I'm showing a little bit the scale of the circular carbon that we will need to realize this. I'm using graphs, let's say the projections by the Nova Institute. So of course, these are projections based on what is necessary to achieve global net zero. And they, of course, predict an important decrease of carbon in the energy and transport sector. That's, let's say, understandable. But a big increase on chemicals, and that I think people don't really understand or see that very often. So the amount of chemicals and materials demand will increase, and therefore we will need a lot to ramp up also on the carbon for chemicals. So, they come up with a number around 3,500 million tons of carbon that will be necessary in 2050. And if we look at the breakdown of where this carbon comes from, they come up with a value around 20% biomass, but I like the comment of André before. This comes from a prediction of how much biomass will be available. So if there is more, I guess, the more the better, because to really achieve net zero, they project 25% CO2 base. And this route is simply necessary for the future, but it's extremely expensive. And that is how you also see that this purple area only becomes significant after, let's say, 2040 or something like this. So, a major role of course, recycling, but recycling mostly for materials. So perhaps answering a bit the question before, recycling of bio-based plastics is a major ingredient of this, let's say, making this possible. But of course, we need to make these bio-based plastics possible. So at the moment, we don't really have that much yet. So when we look, this is the projections, but when we look at reality, and this I'm gathering numbers from different reports, so please don't look at them one by one, but the scale or the order of magnitude. So in 2022, only around 4 million tons of carbon in biochemicals, and projections for biofuels globally 10 million tons based on the capacity to produce, which is not yet there yet, as we have seen with DAISY before. So basically, we need to accelerate if we really need this to happen. And the reason why this doesn't happen yet, of course, there is a lot of technology development needs. There is also market issue, policy issues we have talked about, but I also wanted to highlight something that we see often, that we tend to use the fossil benchmark to really assess new technologies. But we have to realize that the current chemical industry was designed based on abundancy of feedstock, so everything is operating steady state, feedstock is available anytime, anywhere, and we make use of economies of scale. And this is very difficult to envision if we based on renewable feedstocks, not only from the energy side of things, but also from the feedstock availability side of things. So we are looking into medium scale industry. So this is more or less bound to be less economic than our reference. So we have to keep the expectations a little bit realistic. So when we talk about biomass, there is always a lot of discussion whether there is enough biomass or not. There was already a lot of discussion there on what is biomass, sustainable biomass. I don't really want to enter into that discussion because this is not my expertise, but I've looked through different, let's say, reports how much biomass is available in Europe. So now we are looking at Europe numbers. And I only want to say, okay, if we more or less make some projections of what is going to be necessary for chemicals and fuels in Europe, there is only one feedstock that is available at the scale that we need. And this availability, so we are looking at lignocellulosic feedstock, so agricultural waste, forest residues, also the bio part of the municipal solid waste is accounted here. But of course, this doesn't account for losses in the conversion step. So this is just the available feedstock. So again, emphasizing the relevance of not only going for let's say lignocellulosic biomass, but also looking into efficiency of the conversion steps. And a side note, in EU language, these type of feedstocks are often called advanced. So I'm not sure if everyone is familiar, but this is advanced biomass. So that brings us to HIGFLY, so the topic of my talk. So in HIGFLY, we are, this is a European project. Here are the partners. Already up front, if I forget to say, this is definitely not all our work, so that I'm here the speaker representing work of a lot of people. And together we are trying to develop a new technology to convert advanced biomass, so lignocellulosic feedstocks, to SAF. So that was, let's say, the main application. But because we do that via furanics, and we know furanics are also very important for chemicals, I really don't want to leave the chemicals out of the picture here. So, but coming back to SAF, so we have seen this morning introduction of DAISY, what type of technologies we have. So here we have on the left the conventional, that's the reference, is the HEFA SAF, so using oil and fats. And again, I think it's also important to realize it's not exactly a fair reference, because as it has been said, and I showed a couple of slides ago, before, there is very little amount of this type of feedstock. So they are ideal to make fuels, but they are not that much. So this type of conversion, yeah, they are right now the reference, but soon we expect that, let's say, advanced biojet fuel technologies will become more abundant. So the second reference, we did that within the advanced biojet fuels, we have the gas and jet or alcohol to jet. So it would be gasification and Fischer-Tropsch, for example, or let's say production of ethanol and then alcohol to jet. And these are viable and very beautiful technologies. but they do suffer from high cost and also a relatively poor carbon efficiency from the feedstock to the final fuel. So in HIGFLY, what we were trying to do is to develop a technology that is distinctively different, but we had the targets to achieve a high carbon efficiency and also, let's say, reducing cost through, let's say, improving the overall efficiency of the process. So this slide was already shown by Andre before. We are, let's say, looking at a process that is not a standalone, so it has to be coupled with the upstream biorefinery, and in that respect, we are relatively agnostic. So that also gives flexibility to HIGFLY technology that we can, in principle, couple with any biorefinery as long as we get the hands on the C5 sugars, and anyways the technology is robust enough to accommodate presence of other streams. Or let's say, in theory, of course, we are doing a lot of research to demonstrate that, but there is nothing inherently impossible about it. So how does it work if we look a little bit into the building blocks? So we start with the C5 streams, and there is a block of reactions that are meant to produce what we call jet fuel precursors, which are furanics. So the slide is a bit small, sorry, but the key building block here is furfural, but also furfural derivatives. And then these precursors are then going to undergo condensation. So you will, let's say, make longer hydrocarbons, of course, condensation, and then hydrodeoxygenation to produce a drop-in fuel. Well, before I said we were targeting higher efficiency, so I want to straight away show some efficiency. Here I'm showing the external hydrogen requirements. So in any process, you need any external hydrogen, not in any, but in this type of processes, you need hydrogen input externally to, let's say, that end in the fuel. And that is more or less a measure of how much energy efficiency, or let's say, the more hydrogen you need, the less, the more energy inefficient was your process, we could say. So for here, I'm referring to the gas-to-jet technology, looking at different reports, and this is a range. You can see between 0.2 and 0.4 tons of hydrogen externally have to be added to make this gas-to-jet, and then for HIGFLY, we have numbers which are slightly below 0.2. So there is an improvement in the efficiency of the process, and then the carbon efficiencies, we are looking into 60, 70, and this is based on, let's say, the numbers that we are getting from the project. So the process, the process, as I mentioned before, so we have here the two pillars. So we get the C5 biorefinery stream, we have the synthesis of the precursors, here in red, the jet fuels, and in between we have also been looking into purifying these precursors, particularly furfural. Furfural, one of the separation is a rather energy-intensive step, so we have been looking into membranes for this. And there is also, let's say, a line of work looking at the catalytic valorization of side streams to overall, let's say, improve the overall performance of the process. As in any European project nowadays, we are also looking, of course, into the assessment of the entire, let's say, process chain. So we have, of course, the technology development, but there is techno-economic evaluations, cost analysis, LCAs. And what we also wanted to do very clearly was look clearly into the biorefinery, so the upstream, so the sustainability of the feedstocks, and how our technology really blends into the biorefineries that are available, and also looking at the jet fuel quality. I cannot possibly show you everything that we have done. So we are 9 partners with a lot of researchers and 4 years of work. So I only want to show some highlights, but you have seen outside we have a lot of posters. So please feel free to go and check the details over there. So first highlight is that this is about the synthesis of furanics, and particularly furfural. I already said this is our key building block. Well, basically, it comes from, let's say, the C5 stream, so via hydrolysis and dehydration. And we were particularly interested in this because although in this project we look for a SAF application, we know that furfural has numerous applications. And we will have a presentation later today, I think, about this. But essentially, furfural is a very strategic molecule to produce in general. So in order to show, let's say, perhaps give relevance to what we have done, I want to also show what are the key bottlenecks. So the main key bottlenecks in the production of furfural is that, well, this is a reaction that happens in acidic conditions. Now I'm getting a little bit into the chemistry, but I try to keep it light. Basically, we produce a soup with a lot of humans, solid things that will block reactors, will prevent you to have a process that runs continuously, and also it will basically eat up a lot of the biomass that you have put in. So around, let's say, only 30 to 50% maybe of the stream that comes in will end up being furfural. So that's a major loss, and that's a problem. Also separation, let's say furfural water mixtures are very difficult to separate, very energy intensive. So therefore this chemical, well, it's simply becoming very expensive to produce, especially if we would like to use it for a fuel. We have been doing research on this topic for some years here at the university, and through, let's say, several years of research, we understood that there are several things that matter in this reaction that could make, let's say, improvement. So I summarize this by catalyst matter, reactor matters, and solvent matters. So we know that if we can improve a catalyst, if we can improve our reactor, and if we can improve or we can add specific co-solvents, we could address the bottlenecks in this reaction. So that's in this particular project, so that we already understood before HIGFLY, but in HIGFLY we wanted to, let's say, take this one step further. So we have been looking in these three pillars separately. Starting from the left, we have been looking into solid acid catalyst. So I mentioned before, this is an acid catalyzed reaction, normally using sulfuric acid, that brings quite some problems and adds cost separation, so add cost into the process. So we were looking into developing, let's say, solid materials which have, let's say, the acidity that is necessary but can be easily recycled and separated. I will not show this is a very busy slide that my partner Marcelo here is right now laughing. I will definitely not explain everything because it's too much. There is also a poster outside, but I do want to say, well, here our partners CSIC in Spain, they have been looking into, let's say, some specific materials with our metal mix oxides, and these materials are very interesting because they provide acidity, they can be fine-tuned with the specific composition, but they are also stable. So they started looking into this, and they tested and characterized something in the order of 40 different materials, and they do some property-activity relationships to really understand what is exactly that my material needs. They have identified a couple of very interesting materials. Some of them are under patent application, so we are not sharing right now here, but this is one of them, which is tungsten niobium mixed oxide. And they have been focusing on also testing the stability of this. So this is one part of the work, but at TUE, besides, let's say, the activity for the reaction, we have been looking for quite some years now into the effect of shaping these reactors, these catalysts in a specific way, so giving them a certain structure. And we know that by doing this, we are able to combine the activity with also, let's say, transport properties that are very important for this reaction. And not only for this reaction, for many others. So what we did in HIGFLY, together with Johnson Matthey, we have been developing coating techniques that can be, let's say, to deposit active catalysts on the surface of 3D materials that have been tested for different reactions. And we also look at TUE into, let's say, modeling to understand how they really work. So in this slide, this is a result we are particularly very happy about. This is done by our student, PhD student Adarsh. Here he is testing in continuous. So this is a normal reactor, a conventional reactor, where we put these materials as a catalyst inside, as a fixed bed. And we produce the reaction, like, let's say we have run the reaction for 36 hours. That's what we are allowed to do in the lab. But anyway, we see a very stable and good performance. So here we achieve something in the order of 70% yields. And what is very important is we see here on the right These are the state-of-the-art systems, and this is our system. So we can improve. This is a very good example of process intensification, where we can see something around 30-fold increase in activity for this system. And very important, we have been doing the work with real feedstocks. So these are not really clean simulated samples, but really feedstocks that come from a biorefinery stream. So moving on to reactors. So this is only a highlight. We have identified already for some time that the mass transfer, let's say the very fast mass transfer rates in reactors are important for this and for many other reactions. And there is a research line here at UE that is trying to valorize this type of reactors. These are high-G reactors that provide extreme fast heat and mass transfer. To valorize them for several applications. And in the past, we had tested them for the synthesis of furfural, but with the, let's say, with the sulfuric acid system. And we had seen a lot of improvement, but they were tested in systems that were not ideal or not in the, let's say, the conditions that we wanted to do. So in HIGFLY, we have been designing and building what we call the next generation of the systems, where we can operate, let's say, with the catalysts that are developed within HIGFLY. And at the moment, the demonstration is undergoing, so I'm sorry, I would be very happy to show some results today, but research is research. It takes some time, but according to our predictions, this will also have a major impact in the reaction. So, as I said, the demonstration is, let's say, planned for the coming months, so we will finish the project with these results. So the other part that I know it's been a little bit intense on results maybe, but I really want to show some of the important things we have been doing. So the other pillar was catalyst matters, reactor matters, and the third one was solvent matters. So we know from the past that using different solvents in this reaction can really benefit. But of course, whenever you start with a new chemical in a process, there are many other side effects. So it's a very thin balance between the effect you expect, but also side effects, of, for example, on the catalysis, or downstream separation, or even, for example, sustainability aspects. So besides doing really trial and error on these things, which we also did and tried to identify systems that were working better, our PhD student working on this topic was really developing, let's say, smart computational tools using machine learning, but also theoretical thermodynamic models to really predict performance and accommodate the complexity of this system and discover new systems. For solvents, we started focusing mostly with deep eutectic solvents, which are, let's say, have a lot of benefits for separation, for example. But throughout the project, we have been also evolving and looking into, let's say, normal or regular solvents. So, well, he did, this is only an example, but he did quite some, let's say, mapping of separation systems, not only looking into furfural, but also furfural derivatives. And from some selected samples or systems, there has also been quite some testing during reaction, but also, for example, XC2 separation of furfural, for example. So, well, I invite you to look into the poster. So I don't want to show results because I would need a full lecture to really see the phenomena that are being seen in this system. But I really invite you to look at the poster here. So, okay, we have produced the furanics. I did skip the whole other part, which was the hydrogenation, or let's say the synthesis of furfural derivatives, because again, that's a lot of time. But let's say we form furfural, we form the furanics. We then have the problem of purifying. For purification, typically furfural in water forms azeotropic mixtures. I'm not sure if you are familiar with this, but it's a very heavily, let's say, energy-intensive separation, which adds a lot of cost and energy to the process. So we have been looking here into membranes and particularly affinity separation systems where you could, let's say, basically separate furfural out of the water with high energy efficiency. Initially in the project, we were intending to look supported liquid membranes. So basically, you would have a porous membrane filled with some, for example, solvents. And although the rational design of this was in principle interesting, that proved very difficult to really materialize in practice. So this is a very nice academic topic, but we quickly moved on into looking into other systems, for example, carbon molecular sieve membranes, where basically we can functionalize the membrane, let's say in a smart way, to separate furfural from water. And we have, let's say, promising results, which we will extend in the coming months or maybe projects. So we have, let's say, the furanics, we have looked into purification. The next step is, of course, to produce the fuel. So let's say from the building block to the fuel. And here we have been looking, so this is the work of partners TNO, Fraunhofer and Johnson Matthey. They were looking into basically two different routes. So one of them starts from, let's say I start from the bottom, from furfural and then condensation into linear alkanes. Sorry. And the second one is starting from cyclopentanone, that's a derivative of furfural, condensation, and then you can get cyclic alkanes, which may be also interesting for the aromatic replacement. So again, here another chunk of work was done, and the main intention, or let's say the main approach followed, was to really try to look at the scalability. So here our partners wanted to see whether the reaction happens, what's the quality of the product, what is the fit that I would have to, let's say, how can I optimize my feed composition? But they didn't want to do it in a lab, simple, let's say, without looking at scalability, but they looked actually into materials that, let's say, catalyst materials that can be commercialized pretty quick. So they are, let's say, already shaped in a let's say, in a realistic setting. And they also have been looking into continuous reactors to see how does this process work with time. Do we have the activation? Do we not have the activation? They have, of course, produced several condensates. These are the liquid samples that you can see here. And then these condensates have been, let's say, hydrotreated to form a jet fuel, or let's say a fuel that we will have to see if it complies with specifications. So here a bit of a summary of the process they have, let's say, developed or thought for the liquid. So for the first one starts with furfural. This is a liquid phase process. So they have a condensation, let's say, in liquid phase, and they propose a two-step hydrogenation, two hydrogenation steps. First, mild hydrogenation, and then deep hydrodeoxygenation, and they get the relatively good yields of linear alkanes. For the other one, you see starting from cyclopentanone, then goes gas phase condensation, and then a one-step hydrodeoxygenation. So here, example of the type of results they collect. So started, let's say, looking at stability, or let's say performance over time, but also how it operates, let's say, with reactivating the catalyst in between. So finally, we get into condensates and fuels, and a very important pillar here of the work that is work done by Sky Energy, Daisy just presented before. And here what they want to see is whether the fuels are actually any kind of close to a jet fuel, and whether it really could fit or meet the specifications that are relevant at the moment. So they have been doing a lot of testing of important properties like volatility, flash points, distillation curves, freezing point, and of course also compositions, if there is oxygen or any other, let's say, elements, metals, etc. The results at the moment, we are collecting some results right now, and we are analyzing them. And pretty soon, I think we will be ready to publish the outcome. But I would say there is light at the end of the tunnel. So, well, the last part. So this. Oh, sorry. This was a lot of, let's say, technology development and assessment of the products, but of course we did also assessment of the process. How does it perform? And here, this is the work of TNO. where they did a lot of process simulation, and they considered a lot of different scenarios. So starting from furfural, for example, I mentioned two scenarios about the condensation, but there were also other scenarios, one solvent, one catalyst, and things like that. So they evaluated different scenarios, and they came up with, of course, some simulations and some numbers. But what I want to highlight now is, of course, some of them were impressively expensive. So you see here, one of the options leads to almost 8,000 euro per ton. So that's very, let's say, unrealistic. So this result shows us this is not the way to go. But there is actually a scenario that is actually very positive. And this scenario leads to around 70% carbon efficiencies. The energy efficiency is also good, but I don't want to report it because it depends on the definition, and then I need another hour to explain. But the price they came up with is, and here I don't really want to look at the number in detail, but at the ballpark figure, because at the end of the day, there is quite some uncertainty in this type of work. But this shows us that the production of this fuel is very close to the market price of HEFA, which is a lot easier process. It requires a lot less processing steps. So this is a very promising number, we believe, and we think there is more research to be done. Also, this type of work shows us what are the main drivers for the cost, where we can improve, and we have some nice ideas. So this is rounding up. We also did environmental assessment. I think I'm already off time. Environmental assessment, and here, of course, we focused a lot on saving of CO2 emissions. A lot of uncertainties in this type of studies. I would have to give the word to my LCA colleague in IFEO. But basically, we show some scenarios present a very good reduction of CO2. But we do depend a lot on data that comes from the upstream biorefinery, which at the moment we don't have very good quality data about that, based on reports in the literature. But we do see that probably acid hydrolysis or steam explosion are, let's say, ways to go. That seems to point in this direction. There are other insights, for example, the solvents. The solvent choice is an important one, or, of course, heat integration. What we also have done, they also have done, is a lot of environmental impact of other categories. So, of course, we are not only looking at CO2 reduction, but also there are a lot of impact about the use of biomass. So with this, I'm sort of closing my talk. I cannot have let's say, a summary of points, but in a nutshell, I think the process performs, let's say, it's highly efficient. That is reflected in a competitive cost. There is CO2 reductions, details on how much and how to calculate aside. But of course, this is a very interesting process, we believe. But of course, this was TRL 3 and 4. So this is not very mature technology, and we believe there is a lot of work to do to continue. So with that, I would like to thank, of course, the consortium partners for all the work and the nice collaboration. I also want to thank the EU for funding, and thank you very much for your attention.
Okay, thank you, Fernanda. Maybe time for a quick question to her. Some clarifications,
very
discussion
quick.
points. Yeah.
Thank you, Fernanda. Really broad overview of the HIGFLY project. The last two slides were on economics and LCA. Do you use, the LCA was apparently based on green hydrogen. Now the question is whether the economics is also based on green hydrogen, and which kind of hydrogen price you use.
Yes, in both cases, yes. Huh? Yeah, correct.
Which kind of green hydrogen price are you using?
Yeah, here there is a very big uncertainty, I know. Of course, there is a broad range between, let's say, 2.5 and 10 euro per kilogram for green hydrogen. This study assumes there is a well-developed hydrogen economy, so we are looking into, let's say, stabilized prices. So we are not looking at prices today. I'm not really sure the numbers, but I guess in the order of 3-4 euros per kilogram.
Thank you.
Optimistic, but agree.
Okay, thank you.
But nevertheless, it's the same price that is assumed for the HEFA market price.
Yeah, but doesn't need much.
Yeah, exactly. That is true. Correct. Okay.
Thank you. Quick question? Or that?
I really like the route you also developed and improved for vuur vooral, and also the separation part. So the question is, what else can you do with vuur vooral to make, not only a profit out of that, but to do something sustainable in terms of chemicals that you can see that could make a difference?
Yeah. So the route from food for all to chemicals is very broad. We are looking into hydrogenation products. There will be a talk, I think, this afternoon about this specifically. So yeah, definitely we are looking into that for the next step.
Okay, thank you. And thanks again, Fernanda. I think in the program we now have the lunch, and during lunch also there's the poster presentations just outside the aula here to the left. And then we reconvene at 1:30 here in this
Yeah, there is
room.
sufficient time for having lunch and then looking at the posters, so you can also take it.
Can do it both at the same time.
Yes, exactly.
Okay, great. Thanks. Bye.
Bye.